Hello, welcome back to our discussion on nuclear chemistry. This time, we'll discuss on nuclear stability. Last time we talked about balancing nuclear reaction. Then you may ask, how do we know that it will be an alpha particle would be emitted or a beta or an electron capture or a gamma? Okay, this will depend on the stability of the nuclei. A nuclei is said to be stable if it does not decompose spontaneously. Now, before we go into detail on the nuclear stability, let us recall our concept on the atomic structure from your general chemistry. We have learned that from Rutherford theory that the atoms is mostly composed of empty space. When he tried to bombard a gold foil with an alpha ray, he found out only one out of the 20,000 alpha ray that he released or emitted towards a gold foil. Only one out of the 20,000 alpha ray deflected with a large angle. Then he concluded that there must be a massive part of an atom which is passively charged like an alpha ray. And it is located in the center because most of the alpha ray he emitted just passes through and through the gold foil, and he concluded that the atom is mostly empty space and there is in the center, which is called the nucleus, he referred to the nucleus being the center, there is where the mass of the atom is concentrated. So to have an knowledge of that, let us to recall the concept of that. If this is your atom is represented by a sphere whose atomic radius is around 100 picometer, or 1 times 10 to the negative meter, the nuclear radius is only about 5 times 10 to the negative 3 picometer, or 5 times 10 to the negative 15 meter. An analogy was made on the total size of the atom and the size of the nucleus by comparing the football stadium being the size of the atom and the football ball is the nucleus. So that is how they compare it, how tiny the nucleus compared to the total size of an atom. So the enormous high density of the nucleus prompts us to wonder what holds this particle together so tightly. And based on Coulomb's law, like charges repel and unlike charges attract one another. How come that a nucleus which composed of proton and neutron are holding them together? What makes them hold together? You expected based on the Coulomb's law that like charges repel, you expect that proton will repel one another, considering that they are close to each other, considering their size in the nucleus. That is very small portion of the total volume of the atom. Okay, see the comparison of how small the size of the nuclear radius compared to the atomic radius. So being close together and they are the same charge, you expect proton will repel one another. However, this is counteracted by the presence of neutron. And likewise, there are also short-range attractions between proton to proton and proton to neutron and neutron to neutron. The stability of any nucleus is determined by the difference between the repulsion and the short-range attraction. The nucleus disintegrates if the repulsion outweighs the attraction. On the other hand, the nucleus is stable if the attractive forces prevails. The The principal factor that determines whether a nucleus is stable is the neutron to proton ratio. When the number of neutrons is plotted against the number of protons in various isotopes, okay, just like in this graph, the number of protons, which is the atomic number likewise of an atom, is plotted against the number of neutrons on the y-axis. The lower end is linear. Here, you have a 1:1 ratio. These elements has the greatest stability. However, once this region is passed, this becomes curvilinear. The curve begins to take on to 1:1.25:1 ratio for neutron to proton. In the case of zirconium, 90:40. The ratio, the mass number 90 minus 40, that gives you 50 as the number of proton. So 50 divided by 40 is 1.25 for neutron and 1 to proton. So as you go along this line, you have 1.4 neutron to 1 proton. Okay, until you reach the ratio of 1.5 neutron is to every 1 proton. The stable nuclei of the lighter elements contain approximately equal number of neutrons and proton here. So the neutron to proton ratio is equal to 1. These elements has the greatest stability. The stable heavier nuclei here, however, contains more neutrons than protons. With the increasing atomic number, more and more protons are placed in the nucleus. A larger excess neutron is required to overcome the effect of forces of repulsions that maneuver between protons. As a result, the neutron-proton ratio increases with the increasing atomic number until the ratio is approximately 1.5 at the end of this curve. Later in the discussion, we will go in detail how to attain this stability condition and how a nuclei should fall on this band of stability. Moving on, let us summarize the nuclear stability by considering the following pointers. Moving on, let us summarize how nuclear stability is attained. So, an isotope is completely stable if the nucleus will not spontaneously decompose. Elements with atomic number 1 to 20 are very stable. The ratio of 1:1 ratio of protons to neutron, like in the example of carbon-12 has 6 proton and 6 neutron, is stable. Elements with atomic number of 21 to 82 are marginally stable. The 1:1.5 ratio of protons to neutron, like in the example of Mercury 200, has 80 protons and 120 neutrons. Elements with atomic number greater than 82 are unstable and they are considered radioactive. Example is uranium and plutonium. Radioisotopes is a naturally or artificially produced or radioactive isotopes. In order to be a radioisotopes, an element must be above or below the band of stability. Okay, again we have recall. So to become a radioisotopes, the element must belong to the above the band of stability or below the band of stability. Okay, we'll discuss in detail of that later. Okay, what are the factors that determine whether a nuclear is stable? One is the neutron to proton ratio. If the neutron-proton ratio is equal to 1, then the nuclear is said to be stable. If the neutron-proton ratio is not equal to 1, Whether it's less than 1 or greater than 1, then it is not stable. However, based on the band stability here, because it towards in this direction, you have a curvilinear. So we have 1.25 is to 1 for zirconium. 14, 120, you have 1.4. And we have 1.5 here until we reach the end of the curve. Okay, because as the atomic number increases, that means the number of proton increases, we need more neutron to counteract the repulsion between proton to proton. So above the stability belt, we have here the rule. Above the stability belt, the nuclei have higher neutron to proton ratio. To lower this ratio, these nuclei must undergo beta particle emission. And thus, they are called, the nuclei that fall above the stability belt are called beta emitter. Because during the beta particle emission, this leads to an increase in the number of proton and subsequently decrease in the number of neutron. So the neutron is converted to proton and a beta particle. So as the nuclei emits a beta particle, the neutron is converted to proton, hence the ratio of neutron to proton is lowered. An example of beta emitter is your carbon-14 emitting a beta particle to become a nitrogen-14. Okay, here we have, in this case, we have carbon whose atomic number is 6, that is the number of proton. 14 minus 6 is 8, so there are 8 neutron. So if you take the ratio, 8 is to 6, that would give you a ratio of 1.33. So that is greater than 1. To lower the ratio, the carbon-14 has to emit a beta particle. And thus, the product is a nitrogen-14. So when nitrogen with atomic number 7, that is the number of proton, 14 minus 7, that is 7 neutron. And that gives you 7 is to 7 is 1 is to 1. Hence, this nuclei is stable. When carbon-14 emitted a beta particle, it produced a product, a nuclei that is stable, which is nitrogen-14. If the neutron-proton ratio of a nuclei falls below the stability belt, that means that the number of proton is greater than the number of neutron. So, the proton must be converted to the neutron to increase. In the case then where they are above, you have to decrease the ratio. Here, to increase the ratio of neutron to proton, the proton must be converted to neutron, and thus a positron is emitted. Or this can be done by capturing an electron. So the proton will capture an electron from the K energy level. And we have here 1 plus negative 1 is 0. 1 plus 0 is 1. So a neutron is produced when an electron is captured. When a positron is emitted, a proton likewise is converted to a neutron because we have 0 plus positive 1 and 1 plus 0 is also 1. Okay. An example is we have here boron 8. When you emit a positron, the product is beryllium 8. You have 4 plus 1 will give you 5. 8 plus 0 will give you 8 for boron. Or it can be done by electron captured. Okay, boron 8, when captured an electron, 5 minus 1 is 4. and that is beryllium, and 8 plus 0. So when boron, 8, you have 8 minus 5 is 3. So there are 3 neutrons and 5 protons. So 3 is to 5 is below 1. So it is below this 1:1 ratio here. When a positron is emitted or an electron is captured by boron, the product is a beryllium 8. So 8 minus 4, that is 4 neutron and 4 proton. So the ratio is 1:1. So it falls here with 1:1 at the lower portion of the stability belt. Okay. In these two processes, the atomic number decreases by 1 while the mass number remains the same. This is another factor that determines whether a nucleus is stable is the pair principle. Nuclei with even numbers of both protons and neutrons are generally stable. A combination of an odd proton and an even neutron, or vice versa, of a more than 300 stable isotopes, roughly 200 have even number of protons. Only about 120 have an odd numbers of proton and an even number of neutrons. The table here below shows you the number of stable isotopes with even and odd numbers of proton and neutrons. When the number of protons and the neutrons are both odd, they are the least stable nuclei. However, we have 5 stable nuclei that have this type of number of neutron and proton both odd. For example, deuterium, hydrogen. It has 1 proton and 1 neutron. Lithium 6. Lithium has an atomic number of 3. So the mass number is 6. You have 3 proton, 3 neutron. Okay, for boron with atomic number 5, 5 neutron, 5 proton. Okay, nitrogen 14, it is atomic number 7, so 7 neutron, 7 proton. And we have here tantalum with a mass number of 180 and the atomic number is 73. So if you deduct that, 180 minus 73, that gives you 701. Okay, 107 neutrons. Okay, that is odd number of neutrons and odd number of protons, 73. However, what makes this is not equal? In this case, we have 1:1, 1:1, 1:1, 1:1 ratio. But in this case, we have 73. The neutron to proton ratio is 107:73. So we can express that 107, that is 1.46:1. So that is quite stable because if you repair to your band of stability for element 73, so it falls under that slope 1.73. So we have 1.5, 1.4 here. So 1.6, 107 here. 73, 107. So it is between the, it falls, titanium 183 falls within the band of stability. So we have here 5 exemption for the rule that odd number of protons and neutrons are the least stable except these 5 nuclei. Okay. For the odd protons and even or even and odd, they are considered less stable. And we have 50 and 53 isotopes for that. Okay, for even, they're considered stable. And we have 164 isotopes having that even for proton and neutron. Okay, that is for the fair principle. And the third factors that can be considered in determining whether a nucleus is stable is the magic number. Nuclear stability associated with nuclides having number of protons or neutrons equal to the magic number 2, 8, 20, 28, 50, 82, and 126. This magic number seems to indicate the nuclear shells in the same way that the atomic numbers of the noble gases 2, 10, 18, 36, 54, and 86. This is for helium, neon, argon, krypton, xenon, and radon indicate stable configuration. And the fourth consideration is isotopes with atomic number greater than 83. Higher than 83 are radioactive. And these isotope elements having atomic number greater than 83, since they are radioactive, they tend to decay by alpha. Again, if we summarize, those isotopes whose ratio of neutron to proton falls above the stability line of band tends to emit beta particle. And those isotopes of ratio of neutron to proton falls below the band of stability tends to emit positron or electron captured. And isotopes of elements whose atomic number is greater than 83 will emit alpha particle. Okay, for the example on predicting the nuclear stability, we are given here for each pair of isotope listed, predict which one is less stable. Okay, for number 1, we are given lithium 6 or lithium 9 between the two. Okay, we can consider the factors, the neutron to proton, or the pair principle, or the magic number. Okay, we consider everything in determining which one is stable or less stable. Okay, in the case of lithium 6, the number of neutron is 3. The number of proton is 3 as well. So the neutron to proton ratio is 1:1. Although it is add, okay, it is stable for the ratio 1:1. In the case of lithium 9, the number of neutron is 6, the number of proton is 3, which is atomic number. Okay, 9 minus 3 is 6. Okay, the neutron to proton ratio is 6:3, that is 2:1. Obviously, this is less stable than lithium 6. Okay. For the second number, we have here calcium 48. So the proton is 20, the neutron is 28. Okay. If you take the ratio of neutron to proton, that is 28:20, that will give you 1.4:1. In the case of the next element, with scandium 48, the number of proton is 21, the neutron is 48 minus 21, that gives you 27. So the neutron to proton ratio is 27:21, that will give you a value of 1.29:1. You will notice here this lesser, the ratio is lesser than this, but if you will consider the stability band, okay, we have here your calcium 20 and the number of neutron is 28, so above there. Okay, it's above the stability curve or the stability band. Okay, for schedule 21, we have 27. So it's within the 21. It is within the curve or just within the upper limit of the curve. However, we have here add, that is the number of proton and neutron are both add, and this is not included to the stable isotopes under the add. We have only 5, remember, in the pair principle. We have 5 as stable isotopes. We have the deuterium 1, lithium 6, boron 10, nitrogen 14, and tantalum 180. Okay, for the add. So it's that there. Although, and it has 1.29 and the 1.25 start here, so it is not within the slope of the band of stability, although the ratio is small and it is both add the proton and neutron. In the case of calcium, even number of neutron, even number of proton, therefore it is stable, and this is less stable. Okay, because what is asked is the less stable. Okay, for number 3, we have Mercury 195 and Mercury 196. So if you will compute the number of neutron is 195 minus 80, that is 115, and the number of proton is 80. So the neutron to proton ratio is 115 is to 80. That gives you 1.44 is to 1. In the case of Mercury 196, we have the neutron is 116 and the proton is 80 as well. So the neutron to proton ratio is 116 to 80. That gives you 1.45 is to 1. Again, if you repair to your Mercury 80 here, and the number of for Mercury 195, it is 115. So it's here within the band stability. And for 116, it is also within that the band of stability. However, the 195 is odd even, and the 196 is even. So this is stable and this is less stable. Okay, that is how we determine which one is less stable and which is stable. Okay, then to move on to the next item, we have sodium 23. So the number of neutron is 23 minus 11, that gives you 12, and the proton is 11. So the neutron to proton ratio is 1.1 is to 1. Here in this case, we have neutron is 14, proton is 11. So the neutron to proton ratio is 1.27 is to 1. Okay, this is even odd as well. So they don't belong. We cannot consider the pair principle. Now, if you take the position in the stability band, if you have proton 11, neutron 12, given that one, the other one is 11 for the neutron 13, so it's above. So therefore the ratio of 1.1 is to make it stable, so this one is less stable. Okay. For the case of neon 20, the neutron is 10, the proton is 10. So we have the neutron to proton ratio is obviously 1:1. The other case, you have the neutron is 7, the proton is 10. So neutron to proton ratio is 0.7:1. So this is below the stability band. Whereas this 1:1, it is within the stability band. So this is stable. So this is less stable. Okay. Now moving on to the next number, we have bismuth 2089. So the number of neutron is 209 minus 83. That gives you 126. And the proton is 83. So the neutron to proton ratio is 1.52:1. That is 126 divided by 83. Okay. In the case of the next element, we have element 96. That is your curium. Okay. So for curium 242, the number of neutron is 242 minus 96. That will give you 146. And the proton is 96. So if you take the neutron to proton ratio, that gives you 1.52:1. So for the neutron proton ratio, they have the same ratio. So we'll consider the pair principal. These are both even, and this is even odd, so this is less stable, and that makes curium stable. Now to validate that in the band stability, we cannot, because this is only up to 80. Because beyond 80, greater than 80, there are radioisotopes that emit alpha particles. Okay. So moving on to the next set of example for nuclear stability, we're asked to classify each of the following, whether they are a probable stable, a beta emitter, or a positron emitter. Okay. For the first number, we have calcium 20. Okay. For calcium 20, that means the proton is 20, the neutron is 29. So if you take the ratio of neutron to proton, that will give you 1.45:1. Okay, that if we consider the band of stability for 20 with the neutron 29, it is above the band of stability because the ratio is 1.45 neutron to proton, and that it is at this point only at around atomic number 40, where the ratio has is 1.25:1 for zirconium. So the ratio below here is less than 1.25, but this is already 1.45. So therefore, the neutron is greater than the proton, and it is a beta emitter when it is above the stability curve. So for number 1, this is a beta emitter. Okay. Now for the next number, we have phosphorus 28. Okay, the proton is 15 and the neutron is 13. Okay. So obviously the neutron to proton ratio is less than 1. So it is below the stability curve, or this line 1:1. So if we repair to that, 15, proton 15 and 13, it is below the band of stability. And if it's below the band of stability, therefore it is a positron emitter. Okay. Or positive 0. This one is negative 1, 0. Okay. Okay, for the next number, we have, for number 3, we have element 67. That is holmium. Okay. Element holmium 150, the number of neutron, 150 minus 67, that is 83. The proton is 67. So neutron to proton ratio, that is 83 divided by 67, that is 1.24:1. Okay, so let us repair to the stability. Proton 67 here, and the neutron is 83 here. So it is below the band of stability, or the belt of stability, as others may call it. Okay, we have 67 here and we have 83 only. Okay, because towards this the slope is 1.4 to 1.5, and this is only 1.24. The ratio of neutron to proton is 1.24:5, so it's below the band of stability, and it's below the band of stability again. It is a positron emitter. Or positive beta. Okay, moving on to the next number, we have tin 120. So the proton is 50, the neutron is 70. So we have neutron to proton ratio. Okay, we have 70. We divide that with, it is 1.4:1. So let's look on the position of tin. It's within 1.4:1. 50, 70. So this is probably stable. Okay. Now moving on, for the fifth number, we have krypton 90. The proton is 36. The neutron is 90 minus 36. That will give you 54. So the neutron to proton ratio, the 54:36, that is 1.5:1. Okay, let us see if it's within the belt of stability. Okay, you have the atomic number, or the number of proton, 36 here, and 54. So 36, we extend that to 54 here. It's above, and the ratio is 1:5. The 1:5 is towards the end, at the upper. Okay, the ratio here is between 1.25 to 1.4, and it is in this area the neutron to proton falls. We have 36 46 and 54 here. So it's above the belt of stability, therefore it is a beta emitter. Okay. Now for the sixth example, we have here aluminum. Okay, for aluminum, the number of proton is 13, the neutron is 17. So if you take the neutron to proton ratio, that is 17 is to 13, that will give you 1.31 is to 1. Okay, then, although it's within the limit of 1.5, but it is at the lower atomic number. Okay, so let's see. You have proton 13 here and 17 there. So it is above the belt of stability. The ratio 1.3 and the ratio here is below 1.25 and is greater than 1.25, so it must be around here. Okay, so that is above the belt of stability. Therefore, if it's above the belt of stability, it is again a beta emitter, like number 5. Okay, that is how we identify whether a nuclei will emit a beta or a positron, or it is probably stable. In the first example set, we compare two nuclei, which one is stable by referring to their neutron to proton ratio or the magic number or the pair principle. If it's like in the example number 2, we have both even. Here we have both odd, although this has a lower neutron proton ratio, but they are both outside the belt of stability. So we consider the calcium 48 to be more stable than calcium 48. Likewise, in the case of Mercury, 195 and 196, okay, it is within the limit of 1.5, being on the higher here, 1.5, 1.4, so it's within the belt of stability, but we are asked which is less stable between the two, so we apply the pair principle. We have odd even here, and these are both even, so we consider this more stable than the other one. Okay. In the case of sodium here, 23 and sodium 25, this is more stable because the ratio is 1.1, here is 1.27. Okay. For the case of neon 20 and neon 17, the ratio of proton to neutron to proton here is less than 1, so it's below stability belt. And likewise, it is odd even, but in the case of neon 20, it is 10-10, that is the ratio is 1 to 1, and they are both even, so this is more stable than this, so this is the less stable. Okay, for bismuth and curium, okay, we consider this more stable since they are greater than 82, so they are both considered radioactive nuclei. So we take the pair principle that they are even